us start this section with our Euler's equation of motion. Right? So our topic for today is Euler's equation of motion. So what do we study in Euler's equation of motion? We study fluid flow. Now let us consider that we have the streamline flow that is represented by this figure. All right. So make it a little bit. All right. So let us say that we have this streamline flow. And let us say that we have the small element of cross-sectional area dA. Now the pressure acting from this direction is given by P times dA for this, force acting in this direction for this section is given by P times dA, and the force acting in this direction in this section is given by P plus partial differentiation of P with respect to S ds times dA, right? And let us say that we have this let us say we have the gravity force for this section going straight downwards given by mg, and then along the direction of ds uh, we have an angle of angle subtended given by theta. So the component in this direction is given by mg cos theta, and the distance between these two, the straight distance between these two, is given by ds. So ds is the distance between these 2 points. All right. So how do we proceed now? So in order to proceed this following part, we can write solution, right? So in order to do that, first of all, we need to write the force balance equation. So F net force acting on this body is given by PdA minus P plus del P by del S ds dA, and the gravity force that is mg cos theta. So any F net force that is acting on a mass particle is given by m times as to PdA minus PdA, right, plus del P by del S ds dA minus mg cosine of theta. So this two cancels out, and we obtain mass times acceleration in s direction is del P by del S ds times dA minus mg cos of theta. All right. Now we know that the mass of the body is given by rho times dA times ds. All right. So this is the expression for the mass of any body with a cross-sectional area ds and a small displacement ds. Now, in order to replace, now we need to replace this mass equation with rho times dA times ds times acceleration in s direction is del P by del S times ds times dA minus rho times dA times ds, and then z and cosine of theta. We need to calculate the value of cosine of theta. You can clearly see from the figure that we have this particular figure, a triangle here, where this is the direction of ds, this is theta, this is dz, and this is dx. So we can see that cosine of theta equals to dz by ds. So this is the first expression, right? Now we can consider the follows. So now we can write, we can obviously write this as rho times acceleration in s direction is del P by del S, which is minus del P by del S minus rho dA and ds, sorry, rho z, and we get dz, that is del dz by ds. All right, we get dz by ds, and this is minus. So now we can obviously write this expression as rho times as plus del P by del S plus rho g del Z by del S equals to 0. We know from partial differential that the acceleration of the body is given by v times dv by ds plus dv by dt. So this is the general expression for the acceleration of the body. Now we know that this value of dv by dt is particularly equal to 0 when we have the steady flow. So for steady flow, the velocity does not change when the time changes. There is no acceleration in the fluid particle, so only what remains is this particular term. Now replacing that term in this equation, we get rho times v times dv by ds plus del p by del s plus rho times z del z by del s equals to 0. So we get this expression as rho v dv plus rho times p plus rho z, then we get del s, alright, sorry, del z, alright, so we get del z, and then we also get here del z equals to 0. Now we can divide by rho, then we get del p by rho plus v times dv plus then we get z times del z equals to 0. So this particular expression is known as Euler's equation of motion for fluid flow. Alright, so this is known as Euler's equation of motion for, for fluid flow.